So just to recap, one of the things we observed in the last lecture is that if somehow you're able to construct the state on the left-hand side, so superposition of all the 3-bit strings, or in general the n-bit strings, where the phase factor in front of the string y1, y2, y3 is minus 1 to the inner product between some unknown string x and the string y, the Hadamard transformation, the 3-bit Hadamard transformation will extract that information encoded in the phases and write it out in the bit pattern. So let's work a little bit with these qubits in the Hadamard basis. If you have the state 0 plus 1, and note I'm often dropping the normalization factors. So to make this a normalized state, you would need a 1 over square root of 2 factor across. So there's the implicit normalization factor. If you have 0 plus 1 and you apply the NOT gate, well, 1 goes to 0, 0 goes to 1, so you get superposition of 1 and 0. Of course, that's the same as the superposition of 0 and 1, the same vector. 1 over root 2, 1 over root 2. Now, on the other hand, if you have 0 minus 1 and you apply the NOT gate, that goes to 1 minus 0, which pulls out a phase of minus 1 in front of 0 minus 1. So these are both the eigenvectors of NOT, of the NOT gate, or eigenvectors of the X matrix. The first one is eigenvalue plus 1, the second one is eigenvalue minus 1. And again, this is not just metaphorical, it really is. If you let the NOT gate, so the X gate, and the eigenvectors of this matrix, 1 over root 2, 1 over root 2, which is just the same. And the other, if you multiply this, you'll get, you can always factor out the minus 1. These really are the eigenvectors of this NOT gate with eigenvalues plus 1 and minus 1 respectively. This is just a way of writing it in the Dirac notation. So what if, so let's use that knowledge, and what if we have a controlled NOT gate? What does this give us? Well, if the control bit is 0, as we have up here at the top, well, nothing happens. This is an eigenvector with eigenvalue plus 1. If the control bit is 1, but the second bit is in this state 0 plus 1, that's an eigenstate. It's a plus 1 eigenstate. So you apply the NOT gate to it, who cares? You get back exactly the same state with trivial eigenvalue. It gets a bit interesting. Whoops. It's a bit interesting. Well, okay, so again, here the control bit is 0, so nothing happens. But if the control bit is 1, and the target bit, as we call it, is 0 minus 1, well, 0 minus 1 stays 0 minus 1, but it picks up that phase factor of minus 1. Okay, so this is a 2-qubit state, so it's a 4-dimensional vector space. These are the eigenvectors of the controlled NOT operator in that 4-dimensional eigenspace. Now, of course, there's a degeneracy, so there's an eigenspace of dimension 3, so there's many bases you could pick, but here's 3. You could pick these as your basis vector for the plus 1 eigenspace. So these 3 states generate the plus 1 eigenspace of the controlled NOT. And this vector is the minus 1 eigenvector of the controlled NOT. Again, you could similarly, if you wish, you write C naught as a matrix. Looks like this. You can see it maps, 0, 0, 0, 1, stays the same, and then 1, 0, 1, 1 gets swapped. So for example, right, the first entry is talking about the 0, 0 state, then the 0, 1 state, the 1, 0 state, and the 1, 1 state. If you take C naught times this vector, you get this vector, for example. So you could write these as vectors, and these vectors will have two non-zero entries of plus or minus 1 over root 2 in them. And easily verify these are 4 eigenstates with these eigenvalues. Any questions? Okay, so remember this. If you have a 0 plus one of these, let's call them Hadamard states, or Anne called them the plus minus states, this is the behavior. It's always trivial except for the case of 1, 0, minus 1, and then the 1 picks up a factor of minus 1. I guess another thing that maybe it's not always obvious to people when they first start using this notation. So we have 1, 0, minus 1. After the C naught, it goes to, you might say, well, no, it goes to this. Right? Now, this is equal to it's the same thing. Okay, now in direct notation, it might look rather mysterious, but remember 1 just corresponds to this vector, tensor product with, in this case, minus this vector, right? And this minus sign carries through, and it doesn't matter whether you associate it with the first vector or the second vector, and so on. When you compute the inner product, the tensor product of these two vectors, it doesn't matter where you can just pull the minus sign up front and compute it this way. The minus sign commutes through everything, and you end up with the same result. So physically, it seems counterintuitive because you think physically this minus sign is somehow floating around the second qubit. But it's just as well you could associate it with the first qubit. So now, if you have 0 plus 1, 0 plus 1, and by linearity, whenever you have 0 plus 1 in the target qubit, nothing happens because the NOT gate to 0 plus 1 gives you 0 plus 1 with plus 1 eigenvalue. But the last two states are interesting. So I know what happens to 0 tensor 0 minus 1. It gets output as 0 tensor 0 minus 1. But 1 tensor 0 minus 1, it picks up a minus sign. So 0 plus 1 becomes 0 minus 1. And similarly, this 0 minus 1 becomes 0 plus 1. Again, the eigenvector stays the same. It's an eigenvector. This seems very counterintuitive to people when they first see it. Because we think of the control NOT as something that does nothing to the control bit, but flips the second bit. But that's only true when you look at it in one particular basis, in the computational basis. If you look at the same operation in this Hadamard basis, the second bit is where nothing happens. And the first bit is the one that's effectively flipped, the phase is flipped, if the second bit is 0 minus 1. If this is still seeming mysterious or counterintuitive, it's a good exercise to work through until you convince yourself that this works and it seems straightforward. So we're ready to start building up the tools to solve some interesting, develop some interesting quantum algorithms. Suppose I know how to compute a function f. Let's take the simplest function we can think of. It maps one bit to one bit. And suppose I give you a reversible means for computing it. So there's a 2-qubit input, the input x, and the output register is in some state, let's call it C. So C is either 0 or 1. And the reversible implementation of f simply XORs f at x onto the target bit, onto the second bit. It's reversible because it's its own inverse. If you repeat this twice, f at x XORs with f at x, it cancels out. Now, any questions about how we define this? This is just a reversible implementation of the function f. If instead of putting a definite bit, the state C in the second register, we put the 0 minus 1 state, what happens to it? If f at x is 0, well, nothing happens to it, because you're XORing nothing into the second, you're XORing 0 into the second register, so you're applying the identity gate. However, if f at x is 1, you're flipping that second bit. If you flip the second bit, you pick up a phase factor of -1. So you pick up a phase factor of -1 if and only if f at x is 1. So one way of writing that is -1 to the f at x. So you pick up a phase factor of -1 to the f at x. So again, if f at x is 0, that's just +1. If f at x is 1, this is -1. Everybody comfortable with this shorthand? It seems a bit mysterious again, because it looks like, wait a minute, I'm computing f on the second qubit. Why are you writing it down next to the first qubit? But in fact, this is just a phase factor that can be associated with either the first system or the second system. With respect to this state, it's almost like it's like a global phase. So it doesn't matter if you associate it with the first system or the second system. In general, so Kitaev sort of developed this approach, this eigenvector approach to analyzing some quantum algorithms. Right? You can imagine an arbitrary operator unitary u and some eigenvector of u outside, and some eigenvalue e to the I phi. This is very general. It's unitary. It eigenalizes. It has eigenvectors and eigenvalues. So pick an eigenvector psi and its corresponding eigenvalue e to the I phi. The controlled u, so it's an operator that applies u to the second register of however many bits, if and only if the first bit is 1. So if the first bit is 0, nothing happens. If the first bit is 1, well, then you apply u. And then that means that psi goes to e to the I phi psi. And similarly, we can associate e to the I phi to the first system, if we like. The reason we do that is what if instead of having a control bit being 0 or 1, we have it be 0 plus 1? The 0 picks up a trivial phase factor of +1. The 1 picks up the phase factor of e to the I phi 1. So that what was a global phase in a sense at the top now becomes a relative phase. So Anne told you that global phases are not observable, they're not really meaningful physically. But when you construct them into a relative phase, then they are something that's meaningful and observable. And there's a whole set of algorithms. I mean, Martin's going to teach us about how you can do apply the quantum Fourier transform to estimate these phase parameters. Any questions? Again, feel free to interrupt here. So one important thing to emphasize is, what do you mean by a controlled U? Because this unitary U, when you implement it, you're talking in some way you're firing a whole array of lasers, you're doing some very intense sequence of physical operations to affect this unitary U. And identity, well, you do nothing. And so how are you in a superposition of doing all this macroscopic operations, or not? How do you do that robustly? Well, you don't. I mean, when we say controlled U, we're thinking about it at the logical level. So let's say U is made up of some circuit, right? You have to break U up into some circuit of small gates that we know how to implement. The way you would implement a controlled U is to do a controlled, let's say it's gate G1, G2, G3. You do a controlled G1, a controlled G2, and a controlled G3. So mathematically, the left-hand side and the right-hand side are equivalent. And then you would recompile these very small, your gate set is finite. So the control G for every G in my gate set is finite. You would recompile those control G's back in terms of your gate set and build up the right-hand side in terms of your universal gate set. So it's at the logical layer that we're talking about the control view. We synthesize it, we compile it into the gates in your finite gate set. So that's what we mean when we say do a controlled view, where U is some huge, complicated circuit. We don't literally have a superposition of our lasers firing and not firing. We compile it first, we recompile it back into these very elementary gates that we know how to implement, and we compile those. And logically, it implements the control view. So David Deutsch, in his famous paper in the mid-80s, early mid-80s, defined a problem where there was sort of this quantum speed-up, probabilistically a quantum speed-up, and we're able to make it deterministic, actually. So I'll give you sort of the clean deterministic version. You're given a function that maps one bit to one bit, and you want to know the parity, you want to know the sum of f at 0 and f at 1. Equivalently, you want to know if f is constant. Right? If f is constant, then this parity is 0. If f is not constant, then this parity is 1. The catch is, can you do it with just one query to the function? Classically, you can't, right? Classically, you query the function once, you either get f at 0 or f at 1. And knowing just one bit, you have information, theoretically, zero information about whether the other bit is the same or equal. But this circuit here allows you to compute f at 0 and f at 1 with just one query to the function. So this controlled f is just the way I'm denoting uf. So the input bit is on the first wire, so x is encoded in the first qubit, and it XORs f at x into the second qubit. So what does this circuit do? So we start off from 0, 0 minus 1, and then we apply the Hadamard gate. So we get, and I'm going to drop normalization. For convenience, we get 0 plus 1, 0 minus 1. And then when you apply the UF, what happens? Well, the 0, 0 minus 1 picks up a phase factor of minus 1, f at 0, 0. And the 1 control bit picks up a phase factor of f at minus 1 to the f at 1. That's the net effect. So I've lumped a number of steps in here, but we trace through these steps one by one earlier. This is the net effect. You just apply UF once. Oops, there you go. And now you can notice, just for convenience, let's factor out minus 1 to the f at 0. Because this is either minus 0, minus 1, minus 0, plus 1, plus 0, minus 1, or minus 0, minus 1, right? But let's factor out a minus 1 to the f at 0. So it's 0 plus, and then this you can rewrite as f at 0 XOR f at 1. Take minus 1 to the f at 0 times minus 1 to the XOR of f at 1, f at 0 and f at 1. The f at 0's cancel out, and you're just left with minus 1 to the f at 1. So this is just a very simple factoring out of that phase factor. So notice, we want to know what f at 0 plus f at 1 is. With one query to f, we're able to create a qubit that's either 0 plus 1 or 0 minus 1. It's 0 plus 1 if f at 0 plus f at 1 is 0. It's 0 minus 1 if f at 0 plus f at 1 is plus 1. So the function is constant if this qubit is 0 plus 1, and it's not constant if this qubit is 0 minus 1. So how do I tell whether I had 0 plus 1 or 0 minus 1? We apply the Hadamard gate. So after the initial UF gate, we construct 0 plus or minus 1, where whether it's a minus sign or not depends on whether f at 0 plus f at 1 is 1 or not. Right, when you do the Hadamard gate, that f at 0 plus f at 1 that was encoded in the relative phase now is recorded in the bit itself. And you're left with that. You saw that global phase of minus 1 and f at 0, but that's the part you didn't care about. You didn't care what f at 0 was, you just wanted to know, is it equal to f at 1? So the Deutsch algorithm extracts that one bit of it, so in a sense it's global information about f, right? You've just learned one bit about f. It's constant or not. You still don't know whether it's it's constant equal to 0 or constant equal to 1, or if it's not constant, you don't know which bit is 0. So there's 2 bits of information to be known. This extracts one of them, and it extracts a global bit, one that classically you can't extract. Classically, you just extract the local bits in a sense. You extract f at 0 or f at 1. If you want to learn this global property, like what's the XOR of those bits, you're stuck classically. But quantumly, you can do it with one query. Now, this is where the reversible computing business raises an interesting question. Remember, we're talking about a function, right? This function could be some complicated thing that we compute, right? We don't want to have to go through the trouble of evaluating it twice. Can we get away with just computing this large circuit once? Now, you do have to ask, does it still work if when we implement f at x reversibly? Remember when I said you can implement it reversibly, but there's some garbage lying around perhaps? Like the intermediate computation steps, which we just left there? Does the Deutsch algorithm still work if you leave that intermediate garbage sitting there? Well, let's see if the 0 minus 1 trick works in that case, okay? Let's just say we have the bit x here, 0 minus 1, right, again, that just equals x 0 minus x 1. That's just the expansion of this. And we're going to have an extra bit in here, is that workspace, okay? Let's just wedge in that little workspace that we ignore, because it's just scratched workspace. When you apply the messy version of f, it's a reversible f, but we don't worry about cleaning up the garbage. Say you leave an extra copy of x lying around. Minus this is not hold on, redo this. Is the other button? So I think what let's try this. So you have 0, 0 minus 1. And again, there's an extra workspace there. Plus 1. And that workspace 0, 0 minus 1. And now we go, we compute 0, 0, 0. Minus 1 to the 0, 0. And now we compute f in that reversible way. 0, 0, f at 0, minus 0, 0, 1x or f at 0, plus 1. And let's say in our computation we leave some junk information. In this case, there's only so much junk you can leave because it's 1 bit. So let's just say you leave a copy of the input lying around. 1, that's 1 x or f at 1. Now, what was the trick? Right, we want to be able to say that something breaks down. So you get 0 minus 1 to the f at 0, 0, 0, minus 1, plus minus 1, f at 1, 1, 1, 0, minus 1. So far it looks okay. So maybe it works out fine, but wait a minute. This does not factor as, this is not, for example, equal to minus 1 to the f at 0, 0, plus minus 1 to the f at 1, 1. Tensor anything, tensor 0 minus 1. This is an entangled state, and show this, right? This is very much like a 0, 0 plus 1, 1, or 0, 0 minus 1, 1. Entangled state, so it doesn't factor into this Hadamard state, but I don't know what. It's not going to work out nicely. If you just try, so that's not equal to this pretty state, and if you try to do the Hadamard, tensor the identity and everything else, and you measure, you'll notice you get a 50% chance of seeing 0 and a 50% chance of seeing 1. So it just doesn't work. The reason is because of this nuisance that if this 1 were a 0, right? If I were to erase this information and make that a 0, then it does equal. Then it does equal this. Right? You put a 0 in here. Then it does factor, and the Hadamard gives you the answer. But by the mere fact that this information is left behind, it messes up the quantum interference. And you don't get the right answer. This is analogous to the two-slit experiment, right? Where if you know which path, so you need for quantum interference to occur, right? And this computation to work, you need the two paths that go to the same place to cancel out or add up constructively. But by leaving that junk around, right, the different paths that take you to the same state are distinguishable, so you don't get quantum interference. So it's a problem if when you go to implement an algorithm, you leave this junk information lying around. We need a clean implementation of f at x. So you want x0 going to xf at x with no junk correlated to x lying around. So is that a problem? Actually it isn't. It's one of the things Charlie Bennett developed in his paper, his early work in the early 70s. So I'll sketch the idea. It's really simple in hindsight. So do your messy implementation, reversible implementation of f at x, where you just naively replace each AND gate with the controlled not, and so on. So be sloppy. You keep a copy of the input. You have x, f at x, and there's all sorts of junk correlated with x lying around. Now what do? Copy f at x to an extra register. Keep some extra workspace and copy the answer there. And by copy, we mean implement a controlled knot. Okay, so you're not quantumly cloning here, we're talking about copying a string. So by copy I simply mean, right? So you have a string, I want to have a string say 0, 1, right? It's up here. And I want to have a copy of it down here. So my workspace is blank. You put in a blank sheet of qubits, and then you do a controlled knot here, a controlled knot here. These bits are still here. And 0, control knot, that just leaves it at 0. 1, flips the bit. So you get a copy. Whatever bits are up here get copied down here. So by copying, we simply need to do a sequence of export bitwise controlled knots. So we're going to copy the string up here. So there could be another bit here. It could be a 3-bit thing. You have your bits up here, and you have your extra workspace at the bottom where you just copy the answer. So that's all we mean when we say copy f at x. So you do this messy reversible implementation of f at x the way I described in the first lecture. I copy the answer, and then I run the sequence that maps these bits to these bits, run it backwards. That's the whole point of being reversible. You just you run the circuit backwards, you replace each gate with its inverse gate, and you should get back the input, x, 0, 0. So now you're left with, so x, a bunch of zeros gets mapped to x, f at x, with, the zeros remain 0, so you can factor them out cleanly without interfering with your computation. So a very simple recipe for computing f at x cleanly. This is just a basic result of a classical computation. If you know how to compute something, if you know how to take an input x and produce f at x after some finite number of basic computational steps, then you can easily convert that into a circuit that maps x to f at x with no extra junk lying around. So that's an important aside as you develop quantum algorithms later on. And if you look at Charlie's method, if you have a circuit which uses memory s bits of memory, and has depth t, you notice that the space could blow up as much as an additional t bits. Because every non-reversible gate could add a finite number of extra bits. So your space could blow up proportional to big O s plus t. Your time could double or so, but it doesn't grow up more than a constant factor of t. In some vague sense, this is polynomial overhead, but it isn't so pleasant that you might have an algorithm that uses very few qubits and has big depth, and now your memory requirement blows up as well. But there are space-time trade-offs, so you don't in general need to add so much memory if you want. And there's other subsequent work as well to improve these time-space trade-offs. But just some basic results about reversible computing that are very, very useful as you're doing algorithmic development. Okay. So there's the Deutsch problem, which is very simple. Is this one-bit function constant or not? Together with Richard Joseph, they generalized it into solving a promise problem. You're mapping n-bit strings to 0 or 1 with the promise that it's either constant or what they called, so I'm going to skip this one, just to leave time. So I think we have about another 8 minutes, is that right? Yeah, okay. So I'm going to skip that. So Bernstein-Vazirani posed the problem, or suppose f maps n bits to 1 bit, and f has a very special form. It takes the n-bit string x and takes a dot product with some secret string a. So it's a dot product between these 2-bit strings. So it's a very special function. And you're given a reversible way to compute it. You want to find the n-bit string. The following algorithm does what? Right, the first set of Hadamard gates maps, we know what the all zero string gets mapped to. We know the Hadamard gate maps the bit string x, the sum over all the bit strings with the phase x dot y. If x is 0, the all zero string, then it just gets you get a superposition of all the n bit strings y. So you get, that just prepares a uniform superposition of all the 3-bit strings, say, but in general it works for n bit strings. And then you apply the function, you pick up, again, because you're putting 0 minus 1 in the second register, it computes the function into the phases, as we discussed already. So you get a superposition of all the n-bit strings x with a secret phase of minus 1 to the a dot x. And you want to know a, right? A is classically you need to query this n times to get all those bits. But quantumly, what can you do? Well, we learned by definition, the n-bit Hadamard gate takes such a state and outputs this bit string corresponding to A. So the Hadamard gate was custom built to solve this kind of problem. Right? What I said when I was explaining the Hadamard gate was if you could ever stumble upon such a state, the Hadamard gate will decrypt, will extract that string A for you. And that's how you can solve the Bernstein-Vazirani problem with one query. You can naturally generalize the Bernstein-Vazirani problem in the following way. So first of all, it doesn't have to be bits. You can just have a vector, a tuple of elements in a finite field set P. And it maps n tuples to m tuples, where the vector x gets mapped to some matrix times x. And what their algorithm does, you're given a method for right multiplying by your matrix. This generalization of the Bernstein-Vazirani algorithm allows you to left multiply by the matrix. You put the vector you want to multiply by down at the bottom in the target register, and up at the top in the control registers you get d transpose times the matrix M. And in the Bernstein-Vazirani algorithm, the matrix is just a 1 by n vector. So if you're right multiplying and you want to determine that vector, you need to multiply n times. But if you're left multiplying, you just need one multiple of it and you're done. So this, in a way, generalizes the Bernstein-Vazirani algorithm. A challenge problem is this good for anything? Can you think about a situation where you have a practical means for right multiplying by some matrix, and you would love to have a means to left multiply by that matrix instead? Because this quantum algorithm gives you such a means. So I'm going to... So we have now the raw ingredients to solve the Simon's problem, which I'm about to define. But let me frame this in terms of another property of the Hadamard transformation. Suppose you have a subspace of Z2 to the n. So Z2 to the n is n tuples of binary of elements modulo 2. The orthogonal space to S is simply all the n tuples such that n tuples t such that t dot s, the inner product of t and s is 0 for everything in S. It's a very natural definition of orthogonal space. We define by, let S be a set, right? It's a subset, or subspace. When we take a specific vector y plus s, and we put it in the Dirac notation, it's just shorthand for sum over all the, so in a sense this is a coset. You think of Z2 again as a group, S is a subgroup, y plus s is a coset of S. So it's simply all the elements, it's a superposition of all the elements in S. If you apply the Hadamard transformation to that, you get a superposition of all the elements in the space perpendicular to S. It's useful just to do a very special case of this, which is what Dan Simon did. Okay? So let's suppose you have a subspace consisting of the all zeros vector and some other secret string, S1 up to Sn. Right? These two, this is a subspace, and it's a subgroup or subspace of Z2 to the n. If you give me something of the form x plus x XOR s, you're able to construct such a thing, and you apply the Hadamard transformation to it. What do you get? You get the sum over all y minus 1 x dot y. That's what this one contributes. So what's your amplitude of y? You get y in two different ways. One's from x, one's from x plus s. So you get plus minus 1 this vector dot y. So that's the coefficient of y, renormalized, right? You get 1 over root 2 to the n plus 1 if you do the normalization correctly. So, and this is just a sum over y, it's 1 to the x dot y, 1 plus minus 1 the s dot y. So the only y, so if y dot s is 1, if the inner product of y and s is 1, this vanishes. This 1 and minus 1 cancel out. So the only y's that ever survive are the y's that are orthogonal to s. So you only ever measure, you get a y such that y dot s is 0. So if you sample n plus big O of 1 times, you get all these linear equations, right? You get y1 times s is 0, 2 times s is 0, etc. You can solve linear system to find s. So Simon defined an artificial problem just so we could construct an exponential speedup quantum algorithm. So he said, suppose you have an n-bit function that maps n-bit strings to something, let's say n-bit strings, with the property that f at x equals f at y if and only if x and y produce the same coset of s. Or equivalently, so in the case that I just described, you could take this very special case, f at x equals f at y, if and only if either x equals y or x equals y, x, or s, right? So if and only if they're the same, of course, or they differ by this hidden string s. I think if that's the equivalent way of formulating this. Find that hidden subgroup. In other words, find that hidden mask, that hidden string s. And you're given the access to this function. So, the way Simon's algorithm works ultimately is if you create a superposition of all the x's, f at x's, you'll notice that what you end up getting is sum of, for every distinct x, the pre-image, the first register, looks like this. And you sum over, here you're summing over all x, here you're summing over one representative from each of these cosets. So then Simon said, well, what if you measure this register? Measure f at x register. What's left in this state? If it's left in this state and you apply that n-bit Hadamard gate to it, then you're going to be sampling. At the top you see, you sample vectors t that are orthogonal to that hidden string s. If you keep sampling vectors orthogonal to S, you'll be able to find S uniquely. Okay, there's a generalization of this that I'll just leave for your reference, and Martin's going to talk about it a bit as well. But I want to just wrap up with potential applications of Simon's algorithm. So the first one I know of, there's a paper that says, Simon's algorithm inspired the work presented in this paper. Any idea what this paper was? Shor's algorithm for factoring. He built on Simon's ideas to come up with a factoring algorithm. So there's another interesting paper that applies it to cryptanalysis. There's 3 round Feistel ciphers. You want to create a permutation on 2n bits. And you have at your disposal, you assume 3 permutations on n bits. P1, P2, P3. So it's a classic way of building up these ciphers where you permute the first, the n bits, and then XOR it, the bits on the left-hand side, and so on. You cycle through this and you output 2 n-bit strings. So you have 2 n-bit strings at the input, 2 n-bit strings at the output. That's a permutation of some sort. And that's a permutation corresponding to this 3-round Feistel cipher with internal permutations. Right, the task is decide, permute for you. I give you an operator that does that is either the 3-round Feistel cipher permutation with these internal permutations, or a real permutation on 2 n bits. And you have to distinguish which is the case. So it was shown that this classically takes exponentially many queries to distinguish, so this is a good, in this black box framework, it's a good cipher. But what if you have quantum access to this oracle V that does this permutation? You have to decide, is it doing the Feistel type permutation or a real permutation? So these authors, they very cleverly convert this into a Simon problem. So they define W at X. So W at X, it takes a 2n bit string and outputs an n bit string. So it takes the 2 input bits, but just outputs the S part. That's their definition. And then they let alpha and beta be n-bit strings, and b be a bit. And then they define this function, which is an n plus 1 bit function. So f takes that 1 bit b, an n-bit string a, and it outputs either w a concatenated with alpha, and then XOR beta, if b is 1, or WA concatenated with beta, XOR alpha, if B is 1. So if B is 0, it outputs the top, B is 1, it outputs the bottom. It happens, and you can carefully analyze this, it's not too hard to verify this, that this function, it maps the n-bit string corresponding to BA to the n-bit string corresponding to B prime A prime, if and only if those 2 input strings XOR to a fixed string corresponding to 1 concatenated with Z. And Z is some string, which happens to be P1 at alpha XOR P1 at beta, but that doesn't matter so much. I mean, you need it for it to work. So it's if and only if. So they massaged it to satisfy the Simon property. So it's a 2-to-1 function where there's a very special periodic structure determining which 2 inputs get mapped to the same output. So if it is the 3-round Feistel cipher with that permutation, it'll have the Simon property. So Simon's algorithm will always output vectors orthogonal to that fixed string. In which case, you'll find that fixed string. However, if W is in fact just a random permutation, based on a random permutation, no such pattern, it's exponentially unlikely that you'll pass this test. So the quantum algorithm, if you have quantum access to this permutation, you can distinguish with exponentially high probability whether you have a 3-round Feistel cipher with internal permutations or a random permutation. And classically, it was known you need exponentially many queries to do that distinguishing. So that's a really neat application of Simon's algorithm that I hadn't seen. So the challenge for you is, can you find a way to apply any of the tools you learned today or you're going to learn throughout the week to attack any sort of cryptographic primitive? So for example, this method for taking right multiplication and turning it into left multiplication. Or can you apply this Simon method or the Fourier transform, anything else we can learn this week to attack a cryptographic primitive? I mean, these folk had to do some clever thinking to massage it into a Simon algorithm form. Okay, so we'll stop there and take any questions.